Welcome, everyone. Glad you are here. Today, we will prove a neat formula for partitions into two unlabeled blocks using a simple counting trick and a quick recurrence check. In the last lecture, we learned Stirling numbers of the second kind count set partitions, and we got a powerful recurrence. Today, we will use a totally different tool, a direct counting trick that produces a surprising closed form for the case of two blocks. By the end, you will be able to explain why a partition count turns into a power of 2 minus 1, and you will see a technique you can reuse. Label first, then unlabel by symmetry.
I know the recurrence, but a closed form like that feels almost too nice. Where does a power of 2 come from?
Here is our starting point from last time. To build partitions of size n element n, either joins one of the existing k blocks or it starts a brand new block. Quick reset on the definition. We are counting ways to split the set 1 through n into blocks, and the blocks do not have names. Today, we zoom in on the simplest non-trivial case, 2 blocks. This is where the symmetry trick is cleanest. This is the claim we are proving. The number of 2-block partitions is 2 to the n minus 1 power minus 1.
So we are not using the recurrence to solve it, we are going to count it directly?
Exactly. Then we will circle back and check the recurrence as a consistency test. Here is the surprising part. Partitions usually do not have simple closed forms, but this one behaves like binary choices. The secret is to temporarily give the block's names count easily, then remove the names carefully.
Giving names sounds like cheating. Why is that allowed?
We are not changing the underlying objects. We are just creating an easier counting problem. First, partitions into a named block A and a named block B. Once the blocks have names, each element independently chooses A or B. Independent two-way choices multiply, which is where the power of 2 comes from.
So it is like building a binary string. 1 bit per element?
2 labeled assignments are illegal for us. Everything goes to A or everything goes to B, because we need both blocks non-empty. Finally, we undo the labeling. Swapping A and B does not create a new partition, so we will correct the overcount by a factor of 2. Let us make the counting problem easy first. Pretend the 2 blocks are labeled, so we can sign elements one by one with no ambiguity. When I say labeled, I mean we care which block is called A and which is called B. Together they cover the whole set and they do not overlap. Now comes the key simplification. For each element, you make a simple two-way choice. Nothing depends on earlier choices. Multiply 2 choices for element 1, 2 choices for element 2, and so on for n elements total. That gives 2 to the n labeled assignments.
At this point, we are counting all functions from bracket n to a 2-element set, right?
Exactly. It is the same object. Each element maps to A or to B. Before we correct anything, let us see the labeled counting in a tiny case, so the later divide by 2 step feels unavoidable rather than magical. Our set has 3 elements. Each one will choose A or B, like 3 independent coin flips. To list them cleanly, we encode A as 0 and B as 1. Then every labeled assignment is just a length 3 binary string. Here are all 8 outcomes. Right now, we have not enforced non-empty blocks, and we have not removed the A versus B naming.
I can already see 2 bad ones. All zeros and all ones.
Now, we enforce the rule that both blocks must be non-empty. This is the easiest correction. We literally delete the illegal assignments. There are exactly 2 ways to make one block empty. Put everyone in A or put everyone in B. So from 2 to the n, labeled assignments, we subtract those 2 forbidden extremes, leaving 2 to the n minus 2. This line is just packaging the story into one count, labeled disjoint, covering all elements and both non-empty. Here is the subtle step. We counted ordered pairs, but Stirling numbers count unlabeled blocks, so we must identify assignments that only differ by swapping the labels.
This is the part I worry about. Why divide by 2 and not by something else?
If you only care about the set of blocks, then swapping the names does not change anything. It is the same split of the elements. Crucial detail. Since both blocks are non-empty and disjoint, A cannot equal B, so swapping always produces a different labeled assignment. That answers your question. Every true partition corresponds to exactly 2 labeled versions depending on which block we call A.
So dividing by 2 is really dividing by the size of the swap symmetry.
Now we finish. Start with 2 to the n, subtract 2 empty block cases, and divide by 2 for the A-B swap. That simplifies to 2 to the n minus 1 power minus 1. A good proof also leaves fingerprints. It should match small examples, agree with the recurrence, and connect to another viewpoint, like subsets or binary strings. Plug into the formula. For n equals 3, you get 3. For n equals 4, you get 7. For n equals 5, you get 15. Those match the Stirling triangle values. If we specialize the general recurrence to 2 blocks, it predicts how the 2 block counts should grow from one n to the next. This is the specialized recurrence. For example, at n equals 5, it says take 2 times the previous 2 block count, then add the 1 block count.
And S of n minus 1, 1 is always 1 because there is only one way to put everything in one block.
Here is the same counting in one sentence. Take all binary strings, throw out the 2 constant ones, and then identify a string with its bitwise complement, because complement just swaps the 2 blocks. Equivalently, a 2-block partition is determined by choosing one block A, but choosing A or choosing its complement give the same partition. That is why the division by 2 is exactly right. Let us lock this in with one quick computation and one quick explanation prompt. Try to answer before I do, then compare. Use the formula with n equals 6, 2 to the 5 minus 1, which is 32 minus 1. So the answer is 31.
Nice, and that matches the recurrence pattern too. It keeps almost doubling each time.
Because every unlabeled partition has exactly 2 labelings. Pick which block you call A, and the other becomes B. With both blocks non-empty, those 2 labelings are always distinct, so the overcount factor is exactly 2. Main takeaway: for 2 blocks labeling, creates a simple power of 2 count, and symmetry cleanly removes the labels. This label then unlabel strategy is a core combinatorics move. Thanks for watching this. Subscribe to Thinking in Math channel for this and other interesting math topics. And we always welcome your feedbacks. Leave your questions and suggestions in the comments.